Hello friends, today's question. A particle of mass m is executing oscillation about the origin on the x-axis. Its potential energy is ux is equal to k modulus of x cube, modulus of x whole raised to power cube, where k is a positive constant. If the amplitude of oscillation is a, then its time period t is proportional to, we have to find out how the time period t is related with the amplitude of oscillation, that is given as a. So in this case we are given the potential energy, and instinctively what we do, we try to find out the relationship between the potential energy and force. Okay, because we know that force is nothing but the derivative of the potential energy, and from potential energy we can use the relationship mass into acceleration, and that is going to give us a relationship of, you can say, with respect to time also, time period rather. But the problem lies here. Here the potential energy function is given as k modulus of x raised to power 3. Now if we can say derivate this particular modulus, now we have to do it into two parts. First we are going to take that x is positive, and obviously the derivative will be coming as 3x square, and in the second case we are going to take that x is negative, so its derivative will be coming as minus 3x square. So we can say that their combined derivative can be written as 3x square modulus of x, or in some cases it can be also written as 3 modulus of x whole square and multiplied by x. The problem lies that still the f prime equation, or we can say derivative of that function, this function, is still dependent upon the modulus, and it is a little bit difficult to expand that notation so that we are able to get the relationship between the accelerative part and the potential energy part. Okay, no doubt the answer with that method also will be coming the same, but the approach will be wrong because of the derivative problem. Otherwise it would have been quite easy. You simply derivate it, find out the relationship and get the equation for SHM, and from there you can find out the angular frequency, and then you can find out the time period. But because of this modulus it becomes complicated, so we are not going to use derivative because that creates further complications, and the answer no doubt comes same, but the approach is wrong. This is my understanding from the modulus of the differentiation of this modulus function. And much more easy approach is by using the dimensional analysis. So we can use dimensional analysis, and in this dimensional analysis we are going to start with this time period. Okay, so we say time period, which is represented as t, and its dimensions will be m0, l0 and t1, and the variable you can say which this time is involved with are the mass m, amplitude a and constant k. Okay, so you can say that the variables involved are, first is our mass m and its dimension we can write, which will be equal to m1 l0 t0. Second is amplitude, which is represented as small a, and we can write its dimensions as m0, l1 and t0, and last one is constant k, of which the dimension we are going to find out. the last parameter, which is involved, is constant k, and these dimensions we are going to find out, and then we are going to solve it. So we are given that u of x, which is nothing but our potential energy, is equal to k, and we have here x cube. So we substitute the dimensions of potential energy, which is represented as, for easy we just remove the x part. So we say our energy u will be coming as m1 L2 and t minus 2. This is our energy, and substituting this equation, we can write this as m1 L2 t minus 2 will be equal to k, and here we have our x is the displacement part, so this will be our L cube. So this gives us k m1 L2 t minus 2 divided by L cube. So we get that k will be equal to we have m1, and this will be equal to L minus 1, and we have t minus 2. So these are the dimension of the k. And now we start with our proper dimensional analysis process, which states that T is proportional to mass oblique P, and we have K upon raised to power Q, and we have amplitude raised to power C. So we substitute the dimensions. T was our m0 L0 T1, and mass is our m L0 T0 whole raised to power P, and K we just found out is m1 L minus 1 T minus 2 Q, and A is our m0 L1 T0, and this is our R. So this gives us, we have m raised to power P plus Q, and we have L raised to power minus Q, and we have here, one second, plus R, and here we have T raised to power minus 2Q. And on the left side we have same m0 L0 T1. Now we equate them. We get P plus Q is equal to 0, and we have minus Q plus R is also equal to 0, and we have minus 2Q is equal to 1. So this gives us that our Q is equal to minus 1 by 2, and from here we can write that our R is equal to Q, and which is equal to minus 1 by 2, and our P is equal to minus of Q, so this gives us plus 1 by 2. So therefore we can write that T, we have m was raised to power P, which was 1 by 2, and we have K was raised to power Q is our minus 1 by 2, and we have A, and A raised to power R, which is equal to minus 1 by 2. So therefore you can say T is proportional to square root of, inversely proportional to square root of 1 by A. So from the options available to us, option number A is the correct option. Okay. You can say option A is correct. So this completes the question. Thank you.